Hello, everyone. Thank you all for joining us today. My name is Tim Bruns. I am the Associate Editor of Roads and Bridges Media. On behalf of Roads and Bridges and our sponsor, Aquajet Systems, I would like to welcome you to today's presentation titled Better Bonding with Hydrodemolition, Getting High-Quality Results for Road and Bridge Repairs. In this webinar, we will discuss how a good bond is critical for effective, long-lasting concrete repairs. And achieving a good bond starts with the right method of concrete removal. Over the years, the hydrodemolition method has proven to yield the best bonding and the best overall result. This webinar will cover research about why hydrodemolition is so effective, case studies to show results contractors have achieved, and the latest hydrodemolition and water treatment technology. We're going to get started in just a couple of minutes, but first, a little housekeeping. You will notice on your viewer that you have the ability to ask questions. We encourage you to ask questions, and we'll try to answer as many as we can at the end of the presentation based on time availability. Any questions we do not get to, we will answer offline. Our presenters today are Keith Armishaw and Johan Silfwerbrand. Keith is the Business Development Manager for Aquajet's North American subsidiary. Before joining Aquajet in 2019, Armishaw amassed 24 years of industry experience with the brand as a service technician, service manager, and sales associate through a Quebec-based distributor. He works closely with the regional sales team to grow awareness of Aquajet solutions and enhance customer support with industry-wide educational initiatives that increase understanding of the benefits of hydrodemolition. Johan Silfwerbrand, PhD, is a professor in structural engineering and bridges at the School of Architecture and Built Environment at KTH Royal Institute of Technology in Stockholm, Sweden. With a career spanning nearly 4 decades, he specializes in concrete with a focus on maintenance and repair, overlays, pavements, industrial concrete floors, fiber concrete, self-compacting concrete, and concrete and fire. Silfwerbrand is the co-author of more than 50 papers published in peer-reviewed scientific journals and 230 plus additional papers published at international conferences or in popular science magazines and professional association publications. Among his many contributions to the field, he was involved in the pre-design of a dozen industrial concrete pavements and developed the current Swedish design recommendations for concrete pavements and industrial concrete block pavements. Silfwerbrand earned his doctorate in structural engineering from KTH in 1987. And with that, I would like to turn the presentation over to Keith and Johan.
Hello, everybody. I'd like to welcome you to our webinar on better bonding with hydrodemolition, getting a high-quality result for road and bridge repairs. My name is Keith Armishaw. I am the North American Business Development Manager for Aquajet. I'm pleased to be here with my colleague, Sean Kirkpatrick, who's our Service and Application Specialist, and our special guest today, Dr. Johan Silfwerbrand, who's a professor and researcher who specializes in concrete. Let me tell you a little bit about Aquajet. We're known as the industry leader in hydrodemolition machines and solutions, offering the most complete line of products, including robots, high-pressure pump systems, water treatment, and a full range of accessories that make it possible to remove concrete in virtually any part of a bridge. We're constantly innovating and refining our design to enhance speed, mechanize and increase safety for a variety of difficult applications, and to provide precision and control for concrete removal without the risk of damaging surrounding structures. Infrastructure has been a hot topic in the US market, with large infrastructure bill on the table and a lot of talk about the state of the roads and bridges. So the average or estimated average of an interstate system is around 65 years old, and there's approximately 45,000 bridges that are rated in poor condition. So that means that, in short, there's work to be done, and fast, effective methods to achieve long-lasting repair is critical. Quick note on exactly what hydrodemolition is. high pressure water jetting or hydrodemolition. Several terms are used. You'll hear water blasting, hydrodemolition. You'll hear water jetting technique. So basically what we're talking about is a high pressure water jet that will be penetrating the concrete surface through existing cavities and cracks. The water jet basically blows through there and pushes out the concrete components or pieces in chunks. I see it a bit as rapid erosion of the concrete due to the water jet. And when we expose the water jet longer to the surface, the deeper it goes. And by changing the angle of the water jet, we're able to clean down and underneath the rebar into structure to free the rebar and to have a better bond and the bond and do concrete surface to it. So once we're completed, this is what the work looks like. The water jet has removed the concrete from around the rebar, descaled it, and or removed any concrete that was on it, and it gave a rough surface to, all around the yeah. So why choose hydrodemolition? Well, hydrodemolition or water jetting technique is a method of concrete removal that has been proven highly effective for repairs for several years, for a long time actually. It removes damaged concrete up to 25 times faster than handheld jackhammers, and it's a quieter operation. There's less interference with the concrete structure around with the surrounding structure because we don't have any mechanical impacts. The process basically eliminates silica dust exposure because the whole surface is now wet. So any particles would be contained by the water. There's a labor saving because the machine only requires one operator and maybe a high pressure pump operator and the manager on site. But in general, there's fewer people required for this type of operation. The equipment can handle up to 3,000 bar or 40,000 psi water pressure. And it can also extend the life of the structure or the repair anyway, up to 3 times longer. That's what we've seen from some results. And some of the more important factors from the hydrodemolition are the bonding and cleaning the rebar, exposing the rebar without harming it, without any mechanical impact. And I think the biggest benefit from choosing hydrodemolition is the elimination or reduction, drastically reducing the potential for micro cracks or micro fractures inside there on the concrete. And this is a very, very important factor. And in most cases, that's what defines why we would choose to use hydrodemolition. So with that being said, I will turn it over to our specialist, Dr. Silfwerbrand, to discuss elimination of microfractures, bonding, and extending the life of the repair. So over to you, Professor.
Thank you very much. Good morning, ladies and gentlemen. I would like to thank you for listening. I will share a presentation about better bonding through the water jet technology or hydrodemolition. You can, as we heard, there are several names. This technique. So I have received some questions that I want to answer. What is bonding? What is selectivity? Why is it important to clean before recast after repair? And why are jackhammers damaging the structure, at least partly? So the outline of my presentation is that, first of all, I will focus on the importance of removing the poor concrete. Why should we remove poor concrete, damaged concrete? The importance of receiving good bond between the two layers. Then some differences and similarities between water jetting and jackhammers, pros and cons. I will define selectivity and describe it. And I will speak about the absence of microcracks, which are promoting the bond. The absence of promoting the existence of microcracks are detrimental for the bond. And then how the cleanliness of the surface at the very occasion of the new overlay is promoting the bond, and some words about other factors that are influencing the bond between the two layers. And of course, I will conclude. So why should we remove the poor concrete? Quite often the poor concrete is a deteriorated concrete, and that has a low strength, and it leads also to a reduced load carrying capacity. That's why we need to replace the deteriorated concrete with a new concrete. It also quite often contains a lot of detrimental substances, for instance chlorides from de-icing salt or from the seawater, and that will may damage, perhaps not that much the concrete. It could, but even more the reinforcement, and most concrete is reinforced concrete, and the rebars are destroyed by the chlorides. They are leading to corrosion. And then deteriorated concrete, it is porous, it contains a lot of cracks, and that make it water permeable, and we need to protect the existing structure from this. And then the reinforcement bars, they need to be uncovered and cleaned from rust. And if there has a lot of area that has disappeared due to corrosion, we need to add some more rebars. And it is important to remove all concrete behind the exposed rebars. Otherwise, you will have a rather the local bond will be poor at the area close to the rebar, and that has been shown in tests, which I will repeat for you. So here we made some tests on shotcrete. So we started with the Aquajet technology with slabs. And then we added shotcrete, replacing the old concrete. And we looked at 3 different cases. One with a rather thin overlay, so it was thinner than the cover to the reinforcement. Then one case B, where we have a coinciding interface and reinforcing plane, and then a very thick overlay which was behind the rebars. And the slabs I showed you on the previous slide, it was cut into beams, and then we could define 3 types of beams, A, B, and C, with a thin overlay, with a overlay coinciding with reinforcement plane, and with a thick overlay. And then we had reference beams as well, which were just solid of the old concrete type. And then we tested these as simply supported beams in static loading and fatigue loading. And the interesting thing is here the difference in failure modes. On A, C, and R, we received flexural failure, which is ductile. And on the B beams, we received a brittle shear and anchorage failure. And we always want to avoid the brittle failure. And then we tested also in fatigue, and here is it also interesting to see that B beams they could only resist 10% of the loads of the load repetitions on the other beams, and this shows also that it is problematic to have a coinciding interface and reinforcing plane. So the conclusion is that you have, if you detect the rebars, you need to continue your concrete removal behind the rebar, and the conclusion is that you should be at least 0.2 inches behind, plus the maximum aggregate size. And other things with the importance of obtaining good bond, that it is mandatory for producing a repair structure that carries the load monolithically, that you have a static cooperation between the base layer concrete and the new cast concrete overlay. The monolithic action or composite action, it increases the strength and the stiffness, and decreases the deflection of the structure. Good bond also promotes a crack control, and it prevents water transport along the interface. So here is to show you about the load carrying capacity. If we have bond, we will have a composite action, and if we do not have bond, we will have twice as high stresses and only half the load carrying capacity. And it is the differences are even larger if you look at the deformations. So if you have if you do not have a bond, you will have 8 times higher deflections than if you 4 times. 4 times higher deflections than if you have bond. So it is very important to receive bond if you want the structure to carry load in an efficient way, and also minimizing deflections. And another very important thing with a good bond between the 2 layers is that it leads to a harmless multiple cracking. You may have cracking in your overlay due to restrained shrinkage because the base layer has already shrunk, but the overlay will shrink, and there will be a differential shrinkage, and that could cause some cracking. But as you can see from a test by Carlsvärd in Sweden, north of Sweden, you will receive a lot of very, very tiny cracks, and they are not detrimental for the durability or strength or stiffness or etc. But he also tested debonding, and you see the gray areas here, they are debonded between the 2 layers, and he received rather very early, rather thick cracks. You can see 1 millimeter, which is 0.04 inches. And they are very few, the cracks, but they are fewer but wider. And we do not want such cracks because they will impair the durability of the structure. Another thing is that if you have a lot of poor concrete and it contains a lot of cracks and porous, then if you will have a crack in the overlay, then you will have excess to the entire pore structure, and that could when it is going freezing, you could have the fracture because the ice is larger, in fact 9% larger than water, so that could lead to further damages. Now some words about water jetting versus jackhammers. You can see on the left hand side we have the water jetting technology or hydrodemolition, and on the right hand side we have jackhammers. And here I try to summarize the advantages and disadvantages. If you look at the water jetting, it has a selectivity, which I will define, but short it is that ability to remove poor concrete and leaving the sound concrete intact. Then you will have absence of microcracks. It is very efficient. It cleans the rebars from rust, and you can have remote control, which is good for your working environment. The disadvantages is that you need to take care of the water volumes, and then of course since water can freeze, it may be problems in cold weather, freezing weather. Jackhammers, the advantage is perhaps that you are not using water, and it is possible to use it in cold weather, but you do not have any selectivity. It will introduce some microcracks, the reinforcement could be damaged, and it is a poor labor environment, and of course less efficient. So the advantages on one technology could be the disadvantages on the other one, because they are quite different. And you could also look at some other methods to remove concrete, but like sandblasting, shot blasting, grinding, and milling. But all these are mostly superficial or shallow, and you can see that the depth action is only for milling. It is existing, but on the other hand, milling will provide microcracking also, and water jet technology is the only method that both has a depth action and absence of microcracking. And this is very important. That's why we are going further with this technology. And here is the definition of selectivity: the ability to remove damaged and poor concrete while leaving sound and good concrete unaffected. So this is very important. And the reason why, as we saw in the previous presentation here, we are building up a water pressure inside the concrete. And when the pressure exceeds the tensile strength of concrete, it will crack and crash, and then that will be possible to remove that loose particles. And this technology is more efficient if the concrete is poor, if it is porous, and if it contains a lot of crack, because then you will more water will be introduced, and also the strength of the concrete is lower. And that is the reason why this technology is selective. This is another slide of water jet technology. And I have been researching this since mid-1980s. And this was in Stockholm, the first experience that we made on a field test on a bridge in Stockholm with an Italian equipment. And we also made lab tests, and these tests in 1996 to 1997 was to investigate the efficiency of various machines, water jet machines. And we looked at these slabs, and they were made of two types of concrete, one rather low quality concrete and one rather medium or close to high strength. And they were made in every slab was made in stairs with the lower concrete quality on top and the higher concrete on bottom. Red is high strength concrete here, and blue is low strength concrete. And the aim after the water jet technology was to remove all 20 megapascal concrete and leave all 40 megapascal concrete intact. And we had there were reinforcement meshes or in the slabs, and you can see here is a trial to show you a rather good result. You see there is rather small areas of 20 megapascal concrete, and there are large areas of 40 megapascal concrete after the water jet treatment. And here is in 2D instead. And the quantitative requirement was that you should remove at least 80% of the 20 megapascal concrete, but while leaving at least 30% of the 40 megapascal concrete. And you can see the green area that is where you have fulfilled the requirement. So in one example is that you are able to remove 90% of the 20 megapascal concrete without removing more than 25% of the 40 megapascal concrete. And it might be a little bit, you could see that this could be a little bit challenging, but in fact, it was possible for a couple of equipments to fulfill these requirements. And then I will go to the factors influencing bond, and the main factors are these: absence of microcracks, absence of latence, cleanliness, compacting of the overlay, and curing. And some words of each of these. The first one is the absence of microcracking. The macrocracks are visible cracks for the naked eye, but only at the limit. And so you can see a lower border is something like 0.02 inches. They reduce bond strength substantially. The reason is their detrimental effect on the uppermost layer of the substrate. And by selecting the method of concrete removal carefully, you could prevent the existence of microcracks or introduction of microcracks. And here is a comparison between the jackhammers and the water jet technology in the microscopy. And you can see that you have microcracks on the left-hand side on the surface that has been exposed to jackhammers, but you didn't find any on the water jetted surface. And how you can see here the effect. So I made a test on slabs that were water jetted and others that were jackhammered. And you can see that the failure stress measured on cores, 100 millimeter or 4 inches cores. And you can see we had about 2 megapascal for the water-jetted surface and just 1 megapascal for the jackhammered surface. So this time it was twice as good for the water-jet technology. I could say that in some cases 1 megapascal could be sufficient, but there is also a scatter, and if you want to be safe, I absolutely recommend water-jet technology. And here are some other tests by Bissonnet, a Canadian researcher, and these are from 10 years ago, and you can see that he received similar results, 2 megapascal for the water-jet technology and 1.3 megapascal for the jackhammer technology. So this is a large difference between the water-jet technology and the jackhammers, and the reason for the difference is the microcracks. And here is a measurement by a Belgian researcher in this area, Luc Courard, and he measured the microcracks. And you can see here that J07, J014, and J21, there are 3 jackhammers with 7 is 7 kilograms or 15 pounds. And then heavier and heavier jackhammers give more and more microcracks. But also for high pressure water jetting, he received some microcracking, but to a much smaller extent, and it didn't interfere on the results. Another important factor, the second one, is the cleanliness. The substrate surface has to be free from dust, oil, pollutions, and loose particles. And if you are water jetting the surface, it has to be clean immediately after water jetting to prevent cement paste from adhering to the surface, because in old concrete, quite often you have particles that has not hydrated. And when you have the excess of water, that there is such a risk. So I recommend you to clean the surface immediately after water jetting. But then if it goes some weeks before water jet technology and overlay casting, you should clean it again, because otherwise dust from the construction traffic or environment could have disturbed your surface. And cleaning methods are use clean water with high pressure and a large flow, and exposed rebars must be clean from rust. The second is obtained when using water jet technology. A third factor is the absence of latency layer, and when you are casting concrete, you will have a weak and non-durable material containing cement and fines at the top surface. That is some part of segregation, and that reduces bond strength markedly. But if you are repairing it, you are of course removing this part. But if you are casting also on unaltered concrete parts, then you will have a risk of poor bond there. So I recommend you to at least give a shallow water jet treatment also on the areas that are not damaged, in order to remove the latency layer. And then finally, the main factor number 4, it is not the final, it is 4 out of 5. The compaction is also important, of the compaction of the new overlay. And it's perhaps especially important when you are using water jet technology, because your surface is so rough that you will have valleys that could be trapping air if you are not compacting your concrete carefully. And as an alternative to compaction technologies, you could also use self-compacting concrete with a good result. There are several research reports showing that. The Swedish Transport Administration recommends vibration pokers and vibration platforms. And here is a photo showing this, with vibration poker and vibration screed. And then curing of the overlays is also important, because that will reduce the risk of debonding. It will reduce the shrinkage cracking due to differential shrinkage between the two parts. It will also reduce the risk of plastic cracking due to the very early hours. It will increase the strength of the surface. It will increase the durability of the surface, And if you will want to run traffic on, for instance, a bridge deck without an asphalt layer, then the wear resistance will also be increased if you are curing your concrete properly. And during, I recommend at least 5 days, but if you continue for 1 week, it is even better. And start the curing early, because otherwise you could have the plastic shrinkage cracking. And it could be done by hosing water. And then I have spoken about the main factors. There are also several other factors. So they could be grouped in secondary factors and other factors. Among the other factors, there is roughness. It is a third ranked factor, but I will say some words about it, because a lot of people think that it is the roughness that is the important one. But as you can see here, it is a less important factor. It is a third order factor. And here is how we measured surface roughness in Sweden by using a sawteeth curve. And the distance between the measuring point was 10 millimeters or 0.4 inches. And then we defined the roughness as the double amplitude of the sawteeth curve. And here you can see another example of, you can see that the water-jetted surface is much rougher than the one jackhammered or treated by pneumatic hammers. But here I made a comparison between water-jetting and sandblasting, because these two methods are not introducing any microcracks. And you can see that the roughness is 20 times larger for the water-jetted surface than for the sandblasted one. But still you receive similar results around 2 megapascal. So and that means that the roughness has a minor importance. At least sandblasting is sufficient to provide a surface roughness for promoting bond. A remark on surface roughness. The importance of surface roughness is greatly exaggerated in research reports. In practice, hardly any difference between water jetting and sandblasting has been found, and the possible existence of a threshold value that might be even lower than that of sandblasting. That is possible. So if you make the surface extremely smooth, then perhaps you will not receive as good and as a secure bond as if you have at least a roughness coinciding with the one by sandblasting. And if you want to read more, you could read a chapter about bonded concrete in this book about failure, distress, and repair of concrete structures. That is chapter 8. And there is a RILEM report about bonded cement-based material overlays for the repair, the lining, and strengthening of slabs of pavements. And I think these are just 2 examples. There are much more literature available. And finally, to answer the 4 questions, what is bonding? That is the way of gluing 2 materials together in order to reach a composite action. What is selectivity? That is the possibility to remove poor concrete while keeping the sound one. And why is it important to clean before recast? Because dust may destroy the bond. And why are jackhammers damaging the structure? Because they are causing microcracks that in turn reduce bond. Thank you very much for your kind attention.
So thank you very much, Dr. Silfwerbrand. That was a very interesting presentation. I hope all our viewers enjoyed that. I think it very professional. Thank you very much. So just to recap on what we heard, what we wanted to do is just give you guys a quick view of what has been done over the last year in some projects in hydrodemolition. Just different approach. We heard a lot of a bridge deck mentioning in the project. We would like to show you different applications where hydrodemolition was used on bridge structures, but on the different components of the bridges. So this first case study we're talking about we have is a deck rehabilitation on a project in Richmond, British Columbia, on Highway 99 on the Canby Road overpass. The hydrodemolition contractor here was Nilco Builders. So as you can see in the image on the left side over here is the robot in operation, and on the far right side, the pump system. And so this was going over a major highway, which Highway 99. So the objective was to replace the bridge deck. Well, not replace it, but rehabilitate it. So as you can see in the left-hand picture here, there was many patches across the structure. So it was initially milled to above the rebar. So that removed a lot of the weakened concrete on the top. And obviously, as the professor mentioned, it created some micro cracks, which on the other hand facilitated the hydrodemolition work, which enabled the water to easily penetrate into the concrete surface. What's interesting about this structure is that it was built with precast blocks. So the whole deck is actually, it's like a big Lego block system. So over the girders, there was precast blocks. And what you see in the right-hand side was a joint between two blocks that during the hydrodemolition process actually poked a hole through. And you can see in the center of that image where there was absolutely no bonding because the surface was finished from the factory, from the precast plant like that, and there was very little bonding there. So just the water jet, once it hit there, just pushed that piece right out. So other challenges here, the multiple patches, some failures like this to bond, and the challenge of having these joints every 10 feet on the bridge span, and plus having the bridge joints at an angle, at a 45-degree angle to the highway below it. So in order to complete this work, we had to close, it was done at night, so lane closures were involved to limit the risk of any water debris going through the deck, and they were captured below the deck. And we used our Aquajet 710V robot here. Nilco used that with our PowerPack 700 pump system. On the right-hand side, you can see the results, the end of the hydro once it was cleaned. So you can see the rebar coming up from the precast block and the deck rebar that was freed from the concrete with the hydrodemolition. And on the top of the image, you can notice those red painted lines. Those were the markings we had to identify where all of those joints were between the precast blocks. So once the operator reached those areas, he was able to reduce the pressure of the pump system to limit the risk of puncturing a hole through that weaker area. So in this case, they removed approximately 4 inches of concrete to expose the rebar like this, and an overlay was put on, or after the hydrodemolition was completed. The next case study is a full deck and curb removal. Work was performed on the Old Faithful Interchange Bridge in Yellowstone National Park. The hydrodemolition contractor on this project was our friends at Beartooth Water Jetting out of Montana. The main challenge for this project was to complete the hydrodemolition around one of the most iconic and environmentally challenging locations in the U.S., around Old Faithful in Yellowstone National Park. The thermal features from the geyser ran underneath and next to the road and bridge that Beartooth was working on. As you can see in the image here, the bridge up on the right-hand side, the robot up on top of the bridge performing the hydrodemolition work. On the left-hand side, the pump system, a tarp to collect water, and water was collected and pumped into the water treatment plant, which was down here at the lower portion of the photo. No blast water could leave the site or get into the geyser water. So that was really important for them to contain the water as best they could. The equipment used on this project was the Aquajet 710V robot and EcoClear water treatment plant. Beartooth was originally going to perform just the hydrodemolition work, but once the challenges with water supply and treatment became clear, it was determined that Beartooth would also treat the blast water on site using the EcoClear water treatment system. Working with the general contractor, they're able to contain, recycle, and reuse 100% of the blast water. Hydrodemolition was used on this project due to the reduction or elimination of microfractions on the project. So you can see a great photo on the right-hand side of what was removed on the side of the bridge, and this precision cut that was made on the center here. So very nice work done with the machine. Very impressive. So just a quick overview of how the EcoClear works. So first we have an inlet chamber where the water needs to be pumped in. So we're monitoring the volume of water coming in and the quality, so the turbidity and the pH level. Then we introduce flocculation in the first chamber and adjust the pH level. Adjust the pH by adding CO2, carbon dioxide, to neutralize it. Next, the flock or solid particles settle into the storage hopper, so they go up to the clarifier, and the heavy particles drop down into the sludge storage hopper. And the settled solids are pumped out via an integrated pump that's inside the container. Then we have a secondary pH adjustment, so a final adjustment to the pH to make sure that we're on track for the settings we require. And then we monitor the water quality before discharge. So we're measuring the turbidity of the water and the pH level. So the machine is able to keep the pH between 6 and 9, and the turbidity level between 20 and 40 milligrams per liter. Our next case study is an interior repair on the Anthony Wayne Bridge, high-level bridge in Toledo, Ohio, by a contractor called Kokosing, which is a well-known contractor in the state of Ohio. Kokosing's work involved performing concrete repairs to all the interior surface of the cable anchorage supporting the historic suspended bridge. So around 1,200 square feet of deteriorated concrete was removed at a depth of 12 inches inside the anchorages. So the work here was involved, as you can see, the anchors, the cables coming from the suspended bridge down into the anchorage area here in this structure. So the work was actually performed inside this structure. Very, very particular. Some of the challenges that were faced by Kokosing faced in this project. So access to the work area was limited to a man door at each anchorage, and anchorages were classified as confined spaces. So that means you only had one entry point, one exit point. Concrete removal and replacement were performed at a depth up to 65 feet below ground. And the suspension cables had to be protected from damage at all time and were within 24 inches from the wall surface at the bottom of the anchorage. So here you can see on the right-hand side, access was very limited. You can see the operators going down. They were not suspended, but they had their fall arrest protection there, and the system was anchored to the wall. You can see on the top right-hand side where the ergo was anchored there to do the removal on the wall. You can see here a little bit of removal was done on the right-hand side. So a lot of patchwork involved here in this structure. So due to the access limitation on equipment that could fit inside the anchorage, combined with the fact that the majority of the work to be performed was below ground, Kokosing quickly determined that hydrodemolition was the best solution for the demolition work. They needed something that could operate in a tight space and was small enough to fit through the anchorage doors. And the ergo turned out to be the right solution. So the ergo was a lightweight hydrodemolition robot that can be broken down into small components and reassembled inside the structure, and it runs off of scaffolding pipe. So very simple setup. And on the right-hand side, you can see the controller controls the robot movements, and on the door here is the operator remote. So the operator can see from above, basically overview, keep an overview of the machine operating to ensure that everything is working safely. And here's a quick view so you can understand what's involved with the ergo. So we have the controller, the operator with his radio remote, and we have the ergo climber and the cutting head, which would remove the concrete. And on the right-hand side up here, you see it in action inside its structure. And here's some removal where you can see the exposed rebar. Very nice project. Congratulations to composing and performing this work. This next case study we have is the Pensacola Bay Bridge in Florida, and a hydrodemolition contractor on this project was our friends at Rampart Hydro Services. This bridge was damaged by Hurricane Sandy in September 2020. To repair it, affected sections of the bridge deck had to be removed so that new sections of decking could be connected to the existing bridge sections left in place. You can tell from the image, all those sections fell off or removed or fell off from the actual structure. So the overlapping connection required exposing 2.5 feet of reinforcement steel from the existing deck edge so that the connection reinforced steel to the new deck section could be spliced. Okay. The challenges on this project were the urgency to restore the bridge. Though I think, from what I hear, there was a long detour involved to get around this. The weather, working out in the open water, and the cold, the wind, rough waters were a very challenging project for the operation people on site. So as you can see in the image, the robot in the center, the barges to the right side with the water and collection system. So very, very interesting project. Maximum production was achieved by placing several 18,000-gallon potable water storage tanks on the barge. A containment barge was placed below the removal area to capture debris and water. A series of pumps were placed on supporting barges and ferried to various locations along the 3-mile bridge, where isolated sections of the bridge remained intact. So recharging the potable water supply on the barge required tugboats moving the barge to land-based fill-up stations that were miles away. For this project, they used our Aquacutter's 410A robot and Aquacutter's 710A robot. So they removed up 6.5 to 10 inches in depth and a total of 2,386 feet of exposed edge. So very, very interesting project. Thanks to Rampart for sharing this project. This is a bridge wall replacement in Gothenburg, Sweden. We have a short video on this that will leave that play so we can give you little details on this project.
In the Swedish city of Gothenburg, the company SVB, Swedish Hydrodemolition, is carrying out a bridge repair where the project at hand is to replace the bridge walls. For this job, SVB used an Aquacutter 410A and chose to work with its programmable speed zones to make the cut. This hydrodemolition method made it possible to control the speed of the water jet in different areas and with different lance angles. This way, 2 depths in one cut were made and much time saved. Due to traffic both on and under the bridge, the work must be carried out in a controlled manner to minimize the risk of injury to both people and the surrounding area. To protect the traffic under the bridge, the entire underside was covered with protective steel plates. To maximize the hydrodemolition work, SVB chose to power it with Aquajet's latest high-pressure pump, the EcoSilence 3.0. With this new power pack, SVB could complete the work with reduced fuel consumption, running time and emissions, as well as increased efficiency and low noise levels.
Well, thanks to our Aquajet for sharing that video with us, for our Sweden friends over at Aquajet. This is our next case study, was a project on the Pierre Laporte Bridge in Quebec City. So this bridge is between the south and north shore of the St. Lawrence River. The hydrodemolition contractor, Formax Forage and Siage, is located in the Montreal area. Work was done on the suspended bridge here on the lower part of the image. And the project consisted of replacing the waterproofing membrane. On this project, tight schedule with a total of close to 250,000 square feet or 23,000 square meters of surface preparation had to be done. And in 2 separate closures of 4 days, working 24 hours a day for the hydro demolition work. Other challenges were the water supply on the bridge and managing the equipment and different participants or subcontractors on the project. A lot's involved to get the work done. So you have to coordinate with a lot of people to make sure that it can be completed on time. So they had the full northbound lanes were shut down for a total of 10 days. And then a few months later, they shut down the southbound lane for another 10 days to complete the whole work. What's interesting about this project is the decking. I wanted to point out on the top right-hand side here. So this was a steel grit that you can see. That's all those squares. So that's steel and concrete. So the water jetting technique here used was for surface preparation. So we wanted to remove any existing membrane and clean the surface and assure a good bonding surface for the new membrane, waterproof membrane to go on. And here I have a short video. So the equipment used here was our Aquacutter 710V with a Rotolance system. So it's a rotating nozzle system that is designed for surface preparation, and it used our PowerPack 700 pressure pump system. So here's a quick video just so you can see what that looked like during the process here. So you see the operator and the Rotolance going side to side with our extension kit, which is up to 4 meters. Are 13 feet wide. So they completed the whole surface using this type of equipment with some manual pushing devices also. Nice job on Formax for completing this work on time, on schedule, with the right equipment. So hydro demolition method was used here because it was the best option for this application, and it was able to get the work done on time for this tight schedule. So congratulations. So the hydro demolition method has been helping contractors around the world effectively repair roads and bridges in many challenging scenarios. There's a lot of work to be done in North America. Aquajet is prepared to continue delivering solutions that address job site issues and to share expertise with our customers. We'll be taking any questions you have now, but please feel free to contact us at any time with questions about the method, the equipment, or any particular problem you may have encountered on a project in relation to hydro demolition. So, thank you very much. We're here to answer any of your questions.
Thank you so much to Keith and Johan for your presentation. With that, we will now take some time to answer some questions. So the first question I'm seeing that we have asks, how do you prevent punching through a bridge deck while using hydrodemolition? Does the deck need to have certain characteristics to be feasible for this? And what is the fix if a punch through does happen?
That's a good question. Maybe we can work a little bit on this together. Professor, any comments on that you'd like to start with?
Yes. Normally, if you have a bridge deck and you have a hole, it will not be dangerous for the load carrying capacity of the bridge, because there are several other possibilities to carry the load in a bridge deck. But the problem is, of course, that what is underneath, and that could be dangerous. The thing you need to, I see there is another question also about how do you control the removal if you have a varying strength, or if you have, and then it could also be if the damage is uneven. And the idea with water jet technology is to be able to detect the damages, and that's why it's working selectively. But I think you always have to test the equipment on a certain bridge in order to design which pressure and which flow and which distance and which speed you should have of your equipment in order to to be safe. And if you see that the concrete will be poorer and poorer, and if you have such a punch through, of course you need to stop and make a re-investigation of how the equipment is working on this specific area.
Yes. Yeah, excellent. We've, as you maybe noted in some of the presentations, to answer the question from the equipment side, we always advise that there is a risk. There always will be a risk of punching through a deck, depending on the thickness of it, pressure in different settings, as described by the professor. So I guess it has to be planned that it will happen, and if it doesn't, that's good. Because again, once the high pressure water jet is hitting the surface, and if there's poor concrete, it will find it, and if it's all the way through, it will be through. But there are ways through inspections that we've noted in the field that if you, for example, this bridge deck that we presented with the precast blocks, after the first blow through, we went under and we noticed the construction of it, and we were able to determine where areas where we could reduce pressure or make some changes to the machine to reduce the risk of blow through. So an inspection on site during the work or before, but ideally before the work starts, to view what's there. Is there any you could see it seeping through? There could be cracks or different material there. So then you adjust to that, and obviously you have to plan to have something below it if that's the case. And if there is a puncture, what can be done on site? People sometimes will leave it open and repair it after. Sometimes it's stopped and they'll have a quick grout or something to repair it, a patch in the hole, and then they'll come back at the end and redo that. That's what we see from the field.
All right, great. The next question we have says, based on your field experience, what is the most challenging issue for bridge over water deck removal using hydrodemolition?
I'll answer a bit of that. So as you saw in one of our pictures, in one of our presentations, we showed one project where we were removing a complete deck. In that case, you definitely need a device. Like in this case, they had a barge under the bridge to collect the water and the debris. And contractors typically on site are able to handle this. It's not a big, it's something obviously has to be thought of and organized, but we don't see it as a big challenge. Contractors I've worked with, that we've worked with, have found very good ways to collect water in these situations and collect the debris when working in those type of challenges. So it could be full decking underneath. It could be just a barge over water. It could be a tool that's maintained in place. There's a lot of variables here on that question, and it really depends on the structure and what the full repair is, I guess, of that structure.
Okay, great, thank you.
Johan, you have anything you want to add to that?
No, I think you are better to answer that question.
Okay.
Because it's based on your tremendous field experience.
Okay, great. So the next question we have says, what is the minimum hydrodemolition thickness or depth that you can achieve?
I would assume that means the depth of removal. The machine can be calibrated to remove either for surface preparation, so only a few millimeters, depending on the type of tool. And if we go any deeper than a few millimeters, let's say 5 to 10 millimeters, then we would have to change the tool to get the deeper removal. So depending on the type of tool, we can do really light removal, like, for example, CSP 3 to 4. And then after we can go CSP 10 and deeper on the ICRI surface preparation chips, I would call it. Johan, any Anything you want to add
I
to
mean,
that?
you can theoretically you can use the machine also for cleaning and using much lower pressure than if you want to remove concrete. So I cannot see any limits in on the low side.
Okay, great. I think that's all the time we have now then for questions. Thanks again so much to Keith and Johan for your great presentation and for taking some time to answer our questions. That wraps up our time for this webinar. Any questions we were unable to answer, we will answer offline. On behalf of Roads and Bridges Media and our sponsor, Aquajet, I would like to thank everyone for their participation and for staying engaged. This webinar will soon be archived at the same URL you used today and on roadsbridges.com and can be viewed on demand, so feel free to share it with others. So long, everyone.
Thank you.
Thank you.